Hi everybody, Physics Ninja here. Boy, do I have an exciting video for you today. A couple months ago, I was refereeing my son's soccer game, and nature put on a show for me. Have a look at what was going on that night. Here's a picture of a double rainbow we got right over the field area. It was just the most beautiful thing I'd ever seen. It was just so crisp. The colors were really, really bright, and you could see both rainbows. So actually, it got me thinking about a problem that I looked at a long time ago, and I thought I'd make a video in order to share with my subscribers and everybody else out there who wants to learn a little bit about rainbows. What I like the most about this problem is I'm going to do a little bit of qualitative stuff. We're going to do some geometry. We're also going to do a little bit of physics with Snell's law and have a look at what happens when light enters a water droplet. Then we have to do a little bit of calculus, and at the end you're going to understand at least part of this rainbow in a little bit more detail, so you'll appreciate it a bit more. Alright, like with all my videos, if you like the video, give it a thumbs up, consider subscribing to my channel. Alright, let's get started. Alright, let's have a look at kind of the big picture of what's going on here. So we've got our sun, which is a long distance away, and again it's shining light in a particular direction. Okay, and the way I have it now is I have some rain clouds that are a distance away from me, and when I look at the rainbow, I'm always going to see the rainbow opposite of the sun. So why is that? Well, again, now the sunlight from the sun over here contains all of the colors in the visible spectrum, right? We got red, orange, yellow, green, blue, indigo, violet, and so forth. Here's a giant water droplet right here. And here we're going to have sunlight that is going to strike the surface here of water droplets. Now there's millions and millions of water droplets, but let's just have a look at one in particular. We're going to zoom into this picture in just a minute. All right, so we're going to have light that's going to strike the surface of the water droplet. Some of that light enters into the water droplet, and then there's going to be other physics going on here. There could be reflection from one of the back edges, and some of the light is going to exit this water droplet, and it's going to exit in the direction of the observers, which are illustrated down here. So this is what it looks like over here if I'm going to draw it. Let's just consider the red color. So we have red light here coming in from the sun. Again, that light is incoming like this. It's striking this front surface of the droplet, and part of that light is eventually going to come out, and it's going to end up entering my eye. But it only enters my eye when I'm looking just at the right angle. I do not see red if I look down or if I look above. It's only when I'm looking at that particular angle that I get to see the color red. So why is that? Why don't I see red everywhere in the sky? Okay, so in order to look at this problem, we have to now zoom into this raindrop to really see what's going on and to examine the physics. So let's do that. All right, so we're first going to consider red light, which is incoming here from the left-hand side. And that red light is going to strike the surface of a water droplet. Now, water droplet is characterized with an index of refraction. And for red light, it's approximately 1.331. Now what that means is if I consider that interface here, let me draw a normal, just a direction that's perpendicular to that interface. Now some of that red light actually gets reflected, right? So let's start by defining this angle here as my incident angle, just call it I. And there is some reflection going on, and that angle of reflection is also the letter I. But that light over here never enters my eye, right, which is down over here. So I'm not really concerned about what's going on with the reflected light. What I am more interested in is what happens to the light that enters this rain droplet right here. Some of it is going to enter the rain droplet, and it's actually going to bend. And it bends according to Snell's law. So let's call this the refracted angle, just call it R. And what it looks like is if I have air on the outside, and the index of air is approximately equal to 1, and I have red, the index of refraction for red light over here, which is given by another number, on the inside of the water droplet, Snell's law, if you remember, tells me that light will bend. And I can find this angle or write an equation that links both of these angles together, and it should look something like this. Remember, Snell's law is an index multiplied by sine of the angle. Since we have index equal to 1 on the outside, It simply looks like this for this particular interface. We have sine of I, and again, there's 1 here for the index. I don't have to worry about that. It must be equal to the index of, in this case would be red, multiplied by sine of the angle R. So this is Snell's law applied to this problem. All right, let me go ahead and draw what else happens now. So we have light that enters this raindrop. Now it's going to hit the back surface. Some of that light, not all of it. Again, I'm going to draw another line that is perpendicular to that water surface. Some of this light is going to get reflected. And let me just kind of draw it correctly like this. It's going to get reflected. It's going to look something like this. Now again, if this is the angle R, and you can kind of prove that it is, that means that the reflected light is also going to be the angle R. So what else do we have? Now again, some of the light is going to escape. Some of that red light is going to escape, but again, I'm not too worried about this one because it never enters my eye, which is located over here. So let's not even put that in the diagram because it's just going to complicate things. All right, we have one more region to consider, is this last area here when I'm going from water and I'm going to go back into air. Again, if you kind of look at these angles a little bit, the angle R, you could show that this here is also the angle R. And you're going to have some red light, which is going to exit, and it's eventually going to look something like this. Now, over here, we're going to also have the angle I. And this is what it looks like. So what we have here at the different interfaces is something like this. We have refraction, which happens at the first surface. We're going to have reflection down at the surface away from the sun. And then when I exit the water droplet again, I'm going to have some more refraction, which is the bending of light according to Snell's law. And this is what happens. And now this light is going to enter my eye when I'm looking up at a specific angle. Okay, so this is what our diagram looks like. I'm going to clean this up a little bit, and then we're going to do some geometry to link up some relationships between these angles. And so here's the diagram we had here with red light striking the surface. I've kind of cleaned it up a little bit, and I've added a couple lines. I've added some dashed lines here. This is what would happen if there was no water droplet, right? The light would just continue in a straight line. And actually, when I'm looking up here at an angle, and that's when the red light enters my eye. But again, if I just extend that line of sight, right, the red light appears to be coming from this point all the way back here. My brain doesn't know that light is actually coming from the top and then refracting, reflecting, and then refracting again. Right? When I'm looking up, I'm really looking up at this point, which is kind of beyond that water droplet over here. So really what it looks like is you have an incoming light, and then it kind of gets bent and comes out at a different angle. Okay? And I'm going to call this angle phi. And now we're going to use a little bit of geometry to show that this angle phi, you can actually show that it's equal to 4 times the refracted angle minus 2 times this incident angle. And this is going to be really, really important in order to really understand rainbows. So let's go ahead and show how we can do this. So in order to kind of do this, what you have to do here is we're going to make some triangles, because one thing I remember from high school geometry is that if I add all the angles in a triangle, right, if you sum all of the angles in a triangle, that there has to be equal to 180 degrees. Okay, so let's go ahead and do that. All right, so I made a triangle over here. What else? I'm going to have to give these a name. I'm going to call this beta. And if I've created it correctly, that there should also be beta. I'm going to also call this interior angle over here, since I have another triangle here with 2 letter R's. I'm going to call this angle here alpha, and that means that, again, this one here should also be equal to alpha. What else do we have? Let's kind of label all of these properly. And I think there's maybe one more that I need to do. I guess this last angle down over here, give it a different color over here. Let's call this epsilon. And again, everything is kind of symmetric like that, so it's going to be the same. And that's about it. All right, now let's start writing some relationships based on summing the angles and having those being equal to 180 degrees. I did forget to define one angle, so let me go ahead and do that. Let's define this angle here. I'll define this as gamma. All right, so now we have everything defined. It looks rather complicated, but don't worry about it. We're going to break it down into simpler steps. All right, so we have to write down some relationships here. The first thing I'm going to consider is going to be this triangle right here. It's this one. Okay, so if I consider that triangle there, you should be able to show that. Again, if I add up all those angles, what it should be is that alpha plus 2 times the angle r, that is one triangle. That should be equal to 180 degrees. All right, another triangle, or not a triangle actually in this case. Actually, in this case here, if I consider all of the angles, for example, right here, that make up this full revolution. All right, let's have a focus on those angles here, and what do we get? If I sum up these 3 angles, so the way that that looks like for mathematical expression, it's 2 alpha plus the angle gamma. Again, now it's not equal to a triangle, it's actually a full circle. So you get 360 degrees. All right, this allows me to do a little bit of math here because let's eliminate the angle alpha from one of these expressions. Okay, so let's use expression 1. And if I do that, you just simply get alpha by itself. That's 180 minus 2r. Now we're going to substitute that in expression 2, just call it 2 prime. So you get 2. Now let's substitute this whole expression for alpha. Plus gamma equals to 360. All right, we got to do a bit of math now. So this is, carry that out, distribute that 2, minus 4r plus gamma equals to 360. Look what we have. We have 360 on both sides of the equation. We can cancel that out. All right, so we're going to get to one expression here, is that this angle gamma is actually the same as 4 times this refracted angle r. So this is kind of a good starting point here. We're going to use this expression in just a little bit. All right, there's something else going on now. I want to introduce the angle I into this. Okay. So the angle I, actually, if you have a look at it, the angle I is the one that's defined outside here. It's the angle relative to the normal. You should be able to show, if I look at that diagram, that I is actually equal to this refracted angle plus this angle that I call epsilon. So this is going to be my equation 3. And now the last one, so the last one, bear with me here. What we're going to do now is we're going to look at this giant triangle. All right, we're going to look at that big triangle, because I also wanted to introduce this angle phi, right? Because this is really what I'm trying to show over here, is how that angle phi is related to r and I. So let's use one of these triangles to introduce that angle. Okay, so now you have to sum up all these angles. You have to be a little bit careful. This is probably the trickiest expression. So let's start with this one. This is phi plus. Now you got to add up these 3 angles, right? The 3 angles here are r plus epsilon plus beta. And it's going to be the exact same on the other side. So actually what you could do is you could simply multiply that by 2. Okay? And all that, now I've summed up all the angles in that triangle. That has to be equal to 180 degrees. All right, so let's take this second expression a little bit further. All right, phi plus. Now, look what we have here. We have r plus e right here. But I've already defined that as being the letter I, so let's just do that right now. And you also have the 2 in the front here, right? So you have 2i plus 2 beta, that's the 2 multiplying this term, and all of that has to be equal to 180 degrees. All right, we're just about done now, okay? So let's keep on working with expression number 4, okay? Let's go over here. So we have phi. I'm going to bring everything else on the other side, so I have 180 minus 2b, 2 beta. What else? Minus 2i. Okay, so that's the expression. So let's focus on this second term, or sorry, the first term here on the right-hand side. 180 minus 2b. What is that angle over here? Where is that angle beta? Well, that angle beta is also defined in this other triangle, right? This one right here. And look what that does. Right? If you consider just this green triangle right here, I'm also able to write an expression for the angle. So let me go ahead and do that right here. Actually, let's use the color green since we're working with the green triangle. All right, this looks rather complicated, but again, it's just 2 beta plus gamma equals to 180 degrees. You see where this is going now. All right, so have a look. Not only is gamma equal to 4r, we also get that from this expression. We also get that gamma is, we have another expression for gamma. It's 180 degrees minus 2 beta. Well, that's kind of useful because that's the exact term that appears in my final expression over here. So that's it. Now we're pretty much done. So we're going to prove now that the angle phi is simply equal to 180 minus 2 beta, which is the definition of 4r, and minus 2 times the incident angle. Now this expression might not mean a lot to you right now, and it's just a mathematical expression linking some of the angles that are showing up when we look at light striking a spherical droplet. But now let's go have a look at what happens when we plug in some numbers into this equation. All right, so we really have 2 expressions now that govern what happens to light when it enters this water droplet and when it comes out, right? When it enters the water droplet, we have equation 2, and it's also right here when it comes out. That is Snell's law. It tells us how the light bends. Now, we introduce this angle phi because I'm actually looking up at the sky at a particular angle and relative to the angle at which the light arrives, and I call this angle phi. And we arrive to equation 2 using a bit of geometry. So now, there is nothing particular. I didn't say which angle this was, right? When light comes in from the sun, it could hit the front of the droplet. It could hit at a higher position on the droplet. It could hit down here below, right? The sun is very, very large, and it's striking over this entire surface. So let's go have a look now and start plugging into numbers into both of our equations. What we're doing is we're substituting different angles, and let's have a look at what happens to this angle phi. All right, at which angle does the light actually come out of this water droplet? All right, so here's what I did. I combined both of my expressions here, 1 and 2, okay, in order to eliminate what the angle r is. That was our refracted angle. Okay, so what you could do is use Snell's law here just to write it in terms of only an expression for phi, this outgoing angle relative to the incident one. And this is the expression it looks like. All right, now all you do is you use a calculator, and I plugged in several different values of the incident angle. Okay, so let's have a look at some of those specific rays. Well, what if my incident angle is 0? What does that mean? Here's the water droplet, and I've drawn a whole series of different rays over here. It shows you what happens first at the refraction, the reflected, and then the outgoing ray. But the angle 0 corresponds to that one. In this case here, it simply strikes, and there is no refraction, so it simply bounces off. So the angle phi in that case is 0 degrees. As I move up to 10 degrees would be a little bit higher, right? Maybe somewhere around here. 10 degrees. Now the outgoing angle is 9.9. So that means that this angle here would probably be one of these, right? That would be the outgoing angle. Okay. Have a look at what happens now as I start increasing that. You see that the angle phi also increases. But it does only up until a particular point, right? You see, once you have 50 degrees, you've gone up. Once I hit 60, I'm at approximately 42.3. And then what happens? It's kind of the maximum angle that I could get. And then the angle phi actually gets smaller after that, even though I keep increasing my incident angle. So that is kind of a remarkable thing. And here you could see some of these other red lines over here, some things that happen where that angle phi actually starts getting smaller. Okay? What we've noticed is that this expression actually gives us a maximum value right here. This is the maximum value of this function here. And it can't be any bigger than approximately 42.3. Now again, I've only picked like 11 different degrees or 10 different degrees here, okay? But again, if you have a mathematical expression, we can actually show that there is a maximum value to this function. And I actually made a graph of it so you can see all the angles now. But you're never going to have an outgoing angle phi that is 50 degrees, at least not for red. Okay? It's not possible given the math here. So that's really, really important. Let's graph that function here. So here's the function as a function of I in degrees. And this is what the function looks like. Again, just taking some of the values from the table. Now you can see the actual functional form over here. And you can see that there is a very well-defined value of the maximum, right? This is the maximum of this function. Okay, and that happens to be at approximately, well, again, it's very, very close to 60 degrees, right? It's approximately 60 degrees is when we have that maximum. So let's actually do a little bit of calculus now to prove that the maximum angle, we should be able to get to an expression for the maximum angle. What is that maximum angle? And then we'll do it for red, but if we get to a function here, then we can actually do it for other colors as well, right? Because it depends on what the index of refraction is. Because the index of refraction for red was 1.331. That was for red. But if we put in the value for blue, we're clearly going to get a different angle or a different functional form over here. So let's go ahead and do some calculus now to find what is this maximum valued function. All right, so this is just a little bit of calculus now. If you don't remember calculus, it's okay. We'll walk you through the steps. So to find a maximum, you want to find the derivative of the function, and then you want to set the derivative equal to 0, right? We have to show that it's a maximum, but I'm going to not do the second derivative test here. I'm just going to say that the one value that I'm going to find is going to be the maximum value, and I've shown you that from the graph. So the goal now is just to carry out this math over here. So first thing we have to do is we have to take a derivative of this function. Okay, so this involves the derivative of a function that looks like this. That's an inverse function, right? So imagine we have taken the derivative of something like this, of sine of -1 of a function of I. Okay, this is really what the hardest part of this problem is. And this one, if you don't know, all you have to do is simply look it up. Okay, look it up on a derivative table. You can find that on the internet, and it looks something like this. So it'll be fi squared, that function squared, and then at the end you also have to take the derivative of the function relative to the variable I. So you have kind of two terms here. So let's go ahead now and apply it to this. So we have a 4 in front, and our function is going to be 1 divided by the square root of this entire thing. So it's 1 minus. Now the function I is everything here on the inside of this square bracket. So this is sine of I divided by this index. Okay. If it's red, then it'll be the index of red. And I have to square this whole term. And now you have to take the derivative of the inside of this bracket. Okay. So the derivative of the inside of that bracket, if I differentiate sine relative to I, that simply gives me cos of I, and then it still have an extra index over here, n. The second term is really straightforward. It's simply equal to -2. All right, so actually I'm almost done right now. All you have to do now is just rearrange this expression, okay? So let's bring the 2 on the other side, because again, I want to find the maximum value. All right, so you bring the 2 over here, and I can rewrite this as 4 over square root of 1 minus sine squared of I over n squared. And all of this gets multiplied by cos of I over n. Okay. The best way of doing this now, let's just simplify some of this. I could factor out a 2. And I'm left with 2 on this side. I'll be left with 1 on this side. What you want to do now is maybe bring this whole denominator, bring it on the other side. Okay, and if I do that, and also what I'm going to do is I'm also going to square it, just to get rid of that square root term, because that thing is kind of really difficult to deal with. So I bring it on the other side and I square it to eliminate the square root term. All right, so that becomes this. Now this whole other side, remember I have to square both sides. So I'm going to get a 4 over here, and I'm going to get cos squared of I over n squared. All right, now all you have to do is just start grouping some of the terms together, right? So let me go over here on this side. I'm going to bring this on the other side. So I'm going to have 1 equals 2. What do we get? 4 cos squared I over n squared plus sine squared I over n squared. Okay. You can see you could factor out an n squared term right there. So that's kind of useful. Or it's a 1 over n squared. 4 cos squared. Okay. Instead of writing sine squared, I know I can use some of my trigonometric identities. I can write it as 1 minus cos squared of I. Okay. And that there has to be equal to 1. All right. That's kind of useful because now you have 4 cos of I and minus 1 cos of I. And again, we're going to also start simplifying this expression, maybe bring this on the other side. Okay, so try to get this done on this one page over here. So we have n squared equals to, what do we have? 4 minus 1 gives me 3 cos squared of I, and then plus 1. All right, this is it. Now simply get an expression for cos squared of I, or cos of I if you wanted to. So cos of I at the end of the day is going to be equal to, we're going to have n squared minus 1. Okay. All of this is multiplied by 1/3. And then you either have a cos squared here or you take the square root of everything. Okay. And that's it. Actually, just one page. I think we were able to kind of prove this expression over here. So depending on the index of refraction, and that's all we have here, we can actually substitute and find what cos, or what the angle I is. That'll give us a maximum value for my function over here. So let's go ahead and substitute the values for red and see what we get. So we just solved for the derivative of phi relative to I equals to 0, and I got to this expression over here. So let's have a look at what happens now for the color red. Okay, for red, the index of red, again, I said is approximately 1.331. Okay, so I could substitute that into this expression and then find what the angle I is. And if I do that, I find that the angle I is approximately 59.23 degrees, and that was close to the 60 I had in the table. Okay, what you do then is you substitute it back into the angle phi, and this is going to give me my maximum angle. And if I do that, I get that the angle phi is approximately 42.3 degrees. All right? And that's what you had in the table, which we had at 60 degrees. Okay, but this involves a little bit more math. It's a little bit more more foolproof than just substituting numbers, right? You know the exact value now. Now, if you did blue, for example, right? For example, if I did blue, blue has a different index of refraction. The index of refraction is a little bit bigger. It's 1.343 approximately. And if I do that, what I'm going to find is that the maximum angle for blue is a little bit less. It's 40.7. Okay, it's not as big as red, and that's really important. All right. Okay, so now let's go have and compare both of these water droplets. And hopefully now you'll understand when you look up at the sky, you're only going to see red when you get this specific angle. All right, so for you to understand kind of the color sequence in the rainbow now, and why when you look up at the sky, you see red when you look up at 42.3 degrees. Okay? Again, we spent this whole video here looking at how to calculate it for the color red. Now, from that particular raindrop, right, or from that series of raindrops when we're looking up at the sky, there's also all the other colors there. However, if you look at them, look at this purple over here. This purple is not going to enter our eye. Remember, we found that the angle for the purple was like 40.7. It doesn't bend enough to get into our eye. But there's a whole series of raindrops, right? There's millions and millions and millions of them. Okay? So actually, if you look back a little bit further, again, you got incoming sun from the light over here, and some of those raindrops over there, if I look up, I am going to see purple if I look up at 40.7 degrees. Okay, I'm not going to see the red anymore if I'm looking at a different angle, because what do I see? The red is not going to make it into my eye. It's only when I look up at 42.3 degrees do I see red. There are all the other colors there as well, but they're over my head. I don't see them entering my eye. When I tilt my head down a little bit to 40.7 degrees, I am going to see the purple. I'm not going to see red anymore at that angle because, again, the maximum angle, most of the light is at 42.3 degrees. Okay, there's a little bit of red that gets mixed up there. Okay, but red is always going to be the brightest color in that main rainbow because there are no other colors here that can actually reach that 42.3 degrees. Right? Their maximum angle is smaller than 42.3 degrees. Anyway, hopefully this video shed some light on rainbows. That's kind of an interesting phenomenon, and it doesn't require some very sophisticated tools to appreciate. Right? We did some geometry, we did a little bit of Snell's law, and I mixed in a bit of calculus just to make it kind of more quantitative. All right, thanks for watching, folks. I appreciate your support.